What's up guys, it's Simon Fiaz. In today's video I'm going to be going through equilibrium constant question paper, physics maths tutor, aka chemistry A level. Hopefully, inshallah, I'll get this all done, all these question papers from PMT done before my mocks, which is on February the 5th. That's when they start. We'll see. Question 1, this question about the equilibrium. State and explain the effect, if any, of a decrease in overall pressure on the equilibrium yield of SO3. So, decrease in overall pressure. So if I'm decreasing pressure, it's going to shift to the side with more moles of gas to increase pressure. Therefore, it's going to decrease the equilibrium yield of SO3. Decreases yield. That's the easy part. Decreases yield. The next 2 marks, since it's a 3 marker, you need to be extremely specific. And these type of questions they really like to ask. So, first thing I would say is equilibrium shifts to side with in this case with more moles of gas. So equilibrium shifts to oppose decrease in pressure, aka increasing pressure. Part B, this much of that is mixed with that much of that. When equilibrium is reached, the pressure mixture contains this much of that. Calculated partial pressure. So it says that much of that is mixed with that much of that, and equilibrium is reached, the mixture contains this much of that. Okay, so first thing I have to do is find out the equilibrium moles of SO2. How am I going to do that? Well, I've got SO2, O2, SO3. SO2, O2, SO3. ICE method. Initial moles stands for I stands for initial moles, C is changing moles, E is equilibrium moles. So initially I've got 0.460 of this, I've got 0.250 of this, and then obviously this is initially 0. Then I've got 0.180 of this, SO3. So I've increased, added 0.180 moles, that's a change. So therefore in this case I'm going to minus 0.180. And in this case, I'm going to minus 0.180, but because it's a 1 to 2 molar ratio, I'm going to divide that by 2. So I'm actually minusing 0.9 something. So 0.460 minus 0.180, 0.28. And in this case, 0.250, is it 250? Yeah, 0.250 minus 0.180 divided by 2, 0.16. Now it wants me to calculate the partial pressure of SO2. So what I'm going to have to do now is use the ICE MP method. Mole fraction, partial pressure. The mole fraction of SO2 is going to be the number of moles of SO2, 0.16. SO2, 0.28 divided by 0.28 plus 0.16 plus 0.180 times by the total pressure, 215. I want in kilopascals anyway, so I'm just timesing by 215. However, so now let's do that. 0.28 divided by 0.28 plus 0.16 plus 0.180 times by 215, and I get 97.1. Well, I was going to say, however, we need to times it by 2 because we want 2 moles of SO2, but this is already initial moles of SO2 is that, and then we work with that. So this moles is already of 2 SO2, and you get 97.1 kilopascals. Question C, give an expression for the equilibrium constant Kp for this reaction. Kp, so Kp is going to be, remember with Kp, it's curly brackets, not square brackets. Square brackets is always Kc. You make that mistake, you're not going to get this mark. There's 3 marks in this case, but yeah, you would lose out on a mark. So SO3, the partial pressure of SO3 squared, it's 2 moles of that, divided by the partial pressure of SO2 squared, times by partial pressure of O2. And the reason I don't say O2 squared is because we only have 1 mole of O2 anyway. So that's fine. Then it says calculate the value of the equilibrium constant for this reaction. So I'm already given the partial pressures. So all I have to do now is just substitute it in. And I'll write down my Kp value. So SO3 squared (1.85 times by 10 to the power minus 10 to the power 2 squared) divided by 1.85 times by 10 to the power 2 squared divided by SO2 squared 1.67 times by 10 to the power 2 squared times by 1.02 times by 10 to the power 2. I get 1.20 times by 10 to the power minus 2. Now the units, well, it's going to be, obviously, because I'm working with kilopascals, that's the partial pressure, so it's going to be kPa squared divided by kPa squared times by kPa, so kPa cubed. That is the same as 1 over kPa, and that is the same as kPa to the power minus 1. So that is going to be my final answer. What is the effect on the value of Kp if the pressure is increased at constant temperature? Remember, with Kp and Kc, only temperature can affect. I'm going to say only temperature can affect Kp. So with pressure, it stays the same. Nothing happens. Question 2. Draw a cross on the appropriate axis of the graph and the mixture reaches equilibrium. Mixture reaches equilibrium. It's just going to be somewhere here. Now don't put the X here. It's a very, very easy mistake to do. I would have done that. But yeah, it has to be just on or just below the line of x-axis. And then part B says calculate partial pressure of hydrogen equilibrium. I'm given the total pressure. That's really nice. I'm given, so okay, so I'm gonna have to find out the equilibrium moles. So ICE method again, ICE. I've got, in this case, carbon monoxide, hydrogen, carbon monoxide, hydrogen, and methanol, CH3OH. Initially, I have 0.230 mole. No, it's in this mixture of hydrogen this or ratio. So what I have to do first is I'm gonna do 0.230 divided by 3, and then that is, and then times by 2. No, that won't give me the answer. This is mixed with hydrogen in this ratio. Well, equilibrium mole hydrogen is because equilibrium mixture contains this much of carbon monoxide. Therefore, equilibrium moles of hydrogen is going to be double that, 0.240. And also, now I can work out the total number of moles. So well, for carbon methanol this much. I need to work out methanol. I want to find the partial pressure of hydrogen anyway, but I do need to find the total moles. So 0.230. Total number is going to be 0.47. 0. Because it's going to be 0.240 plus 0.230. Yeah, that is the total moles. Now to find out the partial pressure of hydrogen, I need to work out the mole fraction of hydrogen, which is going to be 0.240 divided by 0.47 times by the total pressure, which is just that. So 0.240 divided by 0.470 times by 1.04 times by 10 to the power 4. I want my final answer in kilopascals anyway, so I don't need to convert it. 5310. Perfect. So the tricky part of this question is understanding equilibrium mixtures this much carbon monoxide, 1 to 2 molar ratio, so therefore carbon monoxide, hydrogen moles, equilibrium moles are going to be carbon monoxide times by 2, so 0.240, and then therefore to find out total moles, it's going to be 0.230 plus 0.470, plus 0.24 to give me 0.47, then mole fraction, partial pressure. Pretty simple. Given expression for the equilibrium constant Kp, curly brackets, it's going to be partial pressure of methanol, partial pressure products over reactants, divided by partial pressure of carbon monoxide, times by partial pressure of hydrogen, but in this case partial pressure of hydrogen we have 2 moles of it, so it's going to be squared. Now the units, well, I'm working with kilopascals, so it's going to be kPa divided by kPa times by kPa squared, so kPa cubed. That will give me 1 over kPa squared, and that is the same as kPa to the power minus 2. So partial pressure of methanol divided by partial pressure of carbon monoxide times by partial pressure of hydrogen squared. It says in Mark Cube, do not allow square brackets. Yes, it has to be curly brackets. And kPa to the power minus 2. Part D. So more carbon monoxide is added to the mixture in part B. The new mixture is allowed to reach equilibrium at temperature T. Say the effect, if any, on the partial pressure and on the value of Kp. When more carbon monoxide is added, new mixtures allowed to reach equilibrium at temperature T. State the effect, if any, on the partial pressure of methanol. So what is it saying? More carbon monoxide. So more carbon monoxide added to the mixture in part B. The new mixture is allowed to reach equilibrium at temperature T. So it's asking me new mixture is allowed to reach equilibrium at temperature T. So it's not telling me temperatures increase and decrease. It's only telling me more carbon monoxide is added. So I'm assuming that that is what we're trying to see if there's any effect on. So if that's true, there's going to be no effect on value of Kp because only temperature can affect value of Kp, and it doesn't tell me if temperatures increase or decrease. It just says new mixture is allowed to reach equilibrium at temperature T. Therefore, I'm assuming this is what I'm working with. Effect on partial pressure of methanol. Well, if more carbon monoxide is added, so more of this is added. Effect on partial pressure of methanol. Well, that's also going to increase because because more effect on more carbon monoxide added to mixture, equilibrium will oppose that, therefore more methanol, and if we've got more methanol, we're going to have a higher partial pressure because methanol partial pressure is just the mole fraction of methanol times by total pressure. Total pressure is going to stay the same, and the mole fraction is going to increase therefore the partial pressure increases as well. State the effect of any of the additional catalysts on value of Kp, no effect. Remember, only temperature can affect value of Kp. Explain your answer as catalyst increases the rate of forward reaction and reverse reaction equally. And forward reaction, we'll just say backwards reaction, and backwards reaction equally. Very messy handwriting, but hopefully you get the point. Catalyst is going to increase the rate of forward reaction, reverse reaction equally, and therefore it's going to have no effect on the value of Kp. And we should know as well, only temperature can affect value of Kp anyway. Question 3a. Calculate the mass in grams of oxygen gas in the equilibrium mixture. This one's a bit of a unique one. It's not asking me for moles. It's not asking me for equilibrium moles. It's not asking me for partial pressure. It's asking me for the mass of a gas. So let's see what we're working with. Sample of sulfur trioxide was heated, allowed to reach equilibrium at a given temperature. Equilibrium mixture contains this much of sulfur dioxide. Calculate the mass of oxygen gas in the equilibrium mixture. Okay. Mass of oxygen gas. Equilibrium mixture contains this much mass of sulfur dioxide. I want to find out the mass of oxygen gas in the equilibrium mixture. So I can't just do 2 to 1 molar ratio, and therefore the mass of gas is going to be 6.02 divided by 6.08 divided by 2. No, because I can only do that with, because that's molar ratios. Oh, so what I have to do here, in this case, I need to work out the moles. That's the only way I can do this. So moles of sulfur dioxide is going to be the mass divided by the MR of sulfur dioxide. Sulfur dioxide 64.1, because I'm pretty sure sulfur is 32.1, oxygen is 16, but there's two of them, so it's 32. 32 plus 32.1 is 64.1. That's the moles of sulfur dioxide. But I want the moles of oxygen, therefore I want to divide this by 2, because 2 to 1 molar ratio, and then I've got the moles of oxygen, but I want the mass of oxygen. Moles is mass over MR. The mass is going to be whatever this number is, the moles of oxygen, times by its MR, which is just going to be 32. Yep, times by 32, and I should get 1.52 grams. And this is very tricky because, you know, if I was doing this, I'd be like, surely I just divided by 2. 6.0 divided by 2 give me, I don't know, 3.04? Yeah, of oxygen gas. But remember, this is the molar ratio, so first I need to work out the moles, and then I can do that. And part B says, it says different masses of sulfur trioxide heated, allowed to reach equilibrium at that temperature. It's in Kelvin, perfect. Amount of substance each this at equilibrium. This is equilibrium moles, that's key. You're giving me Kp, remember Kp, curly brackets, calculate mole fraction each substance at equilibrium. Give the expression for the equilibrium constant Kp. Calculate the total pressure in pascals of this equilibrium mixture. Okay, so mole fraction of SO3. Well, it's just going to be sulfur trioxide 0.320 divided by 0.320 plus 1.20 plus 0.600. And that will give me 0.15. 0.15. Sulfur dioxide 1.2. It'd actually be easier if I just work out the total number of moles instead of just adding them for the total, but it's fine. So it's going to be sulfur dioxide 1.20 divided by 1.20 plus 0.320 plus 0.600, 0.57. 2 decimal places, and then oxygen is just going to be the moles of oxygen, equilibrium 0.600 divided by 0.600 plus 1.20 plus 0.320, 0.28. And then it says, so I've done that, give the expression for Kp. Oh, wait, just the expression, okay. So it's just going to be the partial pressure of SO3. No, it's products over reactants. So this is the products. That's tricky. So SO2 squared but in this case I'm not giving partial pressure, I'm just giving the total pressure. So what I'm going to say is of the pressure of SO3 squared, no, SO2 squared, Kp of SO2 squared times by O2, pressure of O2 divided by SO3 squared. Perfect. And then it says calculate the total pressure in pascals of equilibrium mixture. Now this is really tricky in my opinion. How would I calculate the total pressure of the equilibrium mixture? Well, first things first, I'm going to have to rearrange the equation, because in this case I've got the pressures, right? Kp is that. I need to rearrange it to find total pressure. So what I've got to do is I've got to do Kp times by this divided by P of SO2 squared divided by P of O2, but I don't know the P's, so it's just going to be the mole fraction, and that will give me the pressure. So that's why I include pressure in this case. So it's going to be pressure Kp times by the mole fraction. I'll just let this equal the mole fraction. So pressure is Kp times by that, the mole fraction of SO3 squared divided by the mole fraction of SO2 squared times by the mole fraction of O2. Substitute the values in. I've already got Kp. I've already got the mole fractions, so it's pretty simple. The hard part is just realizing, okay, I've got to rearrange the equation. These are pressures, and then I'll just let lambda equal mole fraction. I rearrange it, and then I substitute the values in. So Kp is going to be 7.62 times by 10 to the power of 5 times by mole fraction of SO3 0.15 squared 0.15 squared divided by SO2 0.57 squared times by 0.28. I want it in pascals. Yeah, I've got it in pascals. So 1.88 times by 1, 2, 3, 4, 5. Always try to give it in standard form if you can. 1.88 times by 10 to the power 5 pascals. Okay, part C says explain how this information can be used to deduce that. Okay, still quite a bit left. To deduce that the forward reaction is exothermic. So I know the reaction at this much, a high temperature, equilibrium constant is this, and a reaction at a lower temperature, equilibrium constant Kp decreases. Well, first I'd state the obvious. Kp is higher at higher temperatures. Reason being, at higher temperatures, more products, high temperatures, more products are formed, equilibrium shifts in forward reaction as more products are formed. Then it says use data from part C to calculate value of Kp at 500 Kelvin. Okay, this one's a bit tricky. It's just a sneaky trick. It's not really tricky actually. Value of Kp at 500 Kelvin. So it gives me the value of Kp at 500 Kelvin as that. But this is for this reaction: 2SO3, 2SO2. All I've gone from here to there is I've just divided it by 2, the number of moles. So the value of Kp is just going to be 3.94 times by 10 to the power 4 divided by 2, which is 1.9. Actually, no, it's not going to be divided by 2 because it's not going to be that. Value of Kp at this because this is at 1050 Kelvin. So I want the Kp at 500 Kelvin. All I'm going to have to do here is therefore I'm going to have to square root this. So it's going to be square root of 3.94 times by 10 to the power 4. That'll give me 198.5. The units, however, of partial pressure of SO2 times by partial pressure of O2, it's not even squared, it's to the power of a half, divided by SO3, partial pressure of SO3, so it's going to be, and I'm not working with partial pressure, I'm working with pascals, because it tells me there, pascals, kp's in pascals, so it's going to be PA to the power 1 times by PA to the power of half, divided by PA, products divided by reactants. This is a product, this is a reactant. What happens in this case is because I'm timesing these, I'm going to add the power, so it's going to be 1 plus a half divided by 1. 1 plus a half, well, 1 plus a half is 3 over 2, so I'm going to have PA 3 over 2 divided by PA. And that's just going to be PA to the power of a half. Reason being, because I'm dividing this, therefore I'm going to subtract the powers. That is imaginary 1, so it's just going to be 3 over 2 minus 1, which will give me a half. This is really tricky. So to find out the value of Kp, I square root this answer. Square root 3.94 times by 10 to the power 4, and then value of the units. I need to do a bit of laws of indices from maths. Okay, and the question 4 says nitrogen reacts with hydrogen in this exothermic reaction, which change increases the equilibrium yield of ammonia but has no effect on the value of equilibrium constant Kp. No effect on the value of equilibrium constant Kp. Well, first thing I can see, add a catalyst. Catalyst, no effect on equilibrium yield and no effect on Kp. Decrease the pressure. Well, if I decrease the pressure, is going to have effect on the value of Kp, because remember, only temperature can affect the value of Kp, but it says no effect on the value of Kp, so it's not going to be that as well. So I'm left with B and D. Increases the equilibrium, both of them, B and D, none of them have effect on Kp, so that's fine. But which one increases the equilibrium yield of ammonia? So if I increase the partial pressure of nitrogen, well, the equilibrium is going to shift opposite, and therefore it will increase the equilibrium yield of ammonia, because it increases partial pressure of ammonia, more products divided by reactant is going to increase the equilibrium yield of ammonia. But if I decrease the total pressure, that's going to have No, it's not going to affect the equilibrium yield of ammonia. In fact, it would probably decrease it. Question 5. So 4B is the correct answer. Question 5. Nitrogen and hydrogen mix in a 1 to 3 mole ratio, left to reach equilibrium. In a flask at a temperature of that, the equation for the reaction between nitrogen and hydrogen is shown. When the equilibrium was reached, the total pressure was that. The mole fraction of NH3 was that. Calculate the partial pressure of each gas in this equilibrium mixture. So I know the mole fraction so what? So mole fraction of NH3 was that 0.80, but I want the mole fraction was that, and mole fraction is its equilibrium moles divided by total number of moles times by the total, no, yeah, it's equilibrium moles divided by total number of moles. Actually, no, I know that the mole fraction of well, I can firstly let's work out a partial pressure of ammonia. It's just going to be mole fraction of ammonia times by total pressure in kilopascals. I get 120. But that's the total pressure was that. So now to find out the remaining pressure, 150 minus 120, that's 30 kilopascals. Right, so I've got 30 between these two. That's the remaining pressure. Therefore, the partial pressure of each gas was a 1 to 3 molar ratio. So it's going to be, add them both up, that'll be 4. 30 divided by 4, that will give me the partial pressure of nitrogen. Perfect, 7.5. And therefore, 120 plus 7.5, do 150 minus my answer, and that is the partial pressure of hydrogen, 22.5. Very, very sneaky. Like, you could go through different pathways, like thinking, okay, I need to find an equilibrium mole, but in reality, no, you don't, because it's giving you the mole fraction. So first thing you do is find out the partial pressure of ammonia, which is very easy. The mole fraction times by total pressure in kilopascals. Then you realize, okay, now I've only got 30 kilopascals of total pressure left, and I know it's a 1 to 3 mole ratio, so therefore it's going to be shared equally between nitrogen and hydrogen. And just divide by the total ratio, you find nitrogen, you find hydrogen by times it by 3. And then part B says give an expression for the equilibrium constant Kp for this reaction. Kp, remember, curly brackets, so it's going to be products NH3 squared. Am I working with partial pressures? Yeah, partial pressures of NH3 squared. Obviously, this 3 should be significantly small. Divided by partial pressure of nitrogen times by the partial pressure of hydrogen cubed. So, partial pressure of ammonia squared divided by the partial pressure of nitrogen times by the partial pressure of hydrogen cubed. And remember, Kp is curly brackets, Kc is the square brackets, but in this it doesn't want Kc, therefore don't use square brackets. Part C, calculate the value of the equilibrium constant Kp for this reaction and give its units. So I already worked out the Kp equilibrium constant expression, so all I have to do now is just substitute my values in. So it's going to be partial pressure of ammonia squared, so 1.10 times by 10 to the power 3 squared, divided by partial pressure of nitrogen squared, 1.20 times by 10 to the power 2 squared. No, that's not squared. Yeah, that's not squared. There's no moles of that. It's only 1 mole, it's not 2 moles. Times by partial pressure of hydrogen, 1.50 times by 10 to the power 2 cubed. And that will give me 2.99 times by 10 to the power minus 3. Its units, well, I'm working with kPa, so it's going to be kPa squared divided by kPa times by kPa cubed, so kPa to power 4, that cancels out and left with 1 over kPa squared, and that is the same as kPa to power minus 2. So I've got 2.99 times by 10 to the power minus 3 and kPa to the power minus 2. Part D says the enthalpy change is this. State the effect of any of the increased temperature value of Kp. So remember, I'm increasing temperature, so it will have an effect of value of Kp. But because I know the enthalpy change is minus 92, delta H is minus 92, because we're still using the same equation. So what will happen? Well, equilibrium, so if I, what does it say, increase pressure, forward reaction is exothermic because delta H is negative, therefore the backwards reaction is endothermic. So if I increase the temperature, it's going to shift to the endothermic direction to oppose the increase in temperature. Okay, so perfect. So first let's go through the justification. So if I increase the temperature as the forward reaction is exothermic, equilibrium shifts to the endothermic direction to oppose the increase in temperature by decreasing temperature. I think that's enough. So what will happen to Kp? Well, therefore I'm gonna have more reactants. So it's going to be products divided by reactants, but Kp partial pressure of nitrogen of ammonia squared divided by partial pressure of nitrogen times by partial pressure of hydrogen cubed. But because I've got more of this, well then Kp is going to decrease. Got a smaller number. So decreases, equilibrium shifts to the endothermic direction to oppose the increase in temperature. Perfect. Or you could say endothermic direction, left hand side, backwards direction. And then question 6 says, oh, backwards, which statement about Kp is correct for this reaction in the gas phase? Okay, so I know delta H is negative, so the forward reaction is exothermic. The value of Kp increases as pressure increases. That's false. Remember, Kp only temperature. Can affect the value of Kp. Just by using that key fact, I can eliminate one option, B. A says the value of Kp is independent of pressure, so it's not dependent on pressure. And part D says the value of Kp is independent of temperature. No, it does depend on temperature. I'm left with A and C. Now I know the answer is going to be A, but I'm just going to go through C. Because the value of Kp is independent of pressure. That's true, because only temperature can increase. So if I increase the pressure, it's independent of it. It's not going to affect it. It's not dependent on it. Pressure. Well, part C is wrong as well, because it's wrong. I'm going to show you now, because the value of Kp increases, temperature increases. Forward reaction is exothermic, backward reaction is endothermic. I increase the temperature, it's going to shift to the endothermic direction to oppose the increase in temperature, aka decreasing the temperature, the left hand side, the backwards direction. Therefore, I'm going to have more reactants. So I'm going to have, let's say the product was 10, and originally this was 2. But once I increase the temperature, I've got more reactants. So I go from 10, and numerator, that's the same, but the denominator increases to 5. Which one's a bigger number? It might look like this is a bigger number because you've got bigger that. It's a smaller number. It's 2, that's 5. And this is once I've increased temperature, so the value of Kp will decrease. Question 7. Lot of information. I don't think any of that's relevant. It says use the enthalpy change for the reaction. That's the enthalpy change, and data from table to calculate a value for the HH bond enthalpy. So mean bond enthalpy and any enthalpy required to break bonds. energy required to break bonds minus energy released when new bonds are formed. So I need to do, well, delta H is minus 49, so it's going to be minus 49 equals energy required to break bonds, carbon monoxide, carbon dioxide, so 743 plus 743, I've got 2 moles of them. I mean, carbon dioxide, I've got this, so I've got 1 CO and another CO, plus 3H2, but that's what I'm trying to find, so I'm going to leave that there. Minus energy released when new bonds are formed, methanol, CH3OH, so CH3 OH, so I've got CH 3 times, 412 times by 3, plus CO 360, plus an OH 463, and then plus your H2O, or water H2O, so it's going to be 463 times by 2. Yeah, 463 times by 2. So what I would do here is, first let's work out what 743 plus 743 is. 1486 plus 3, let HH equal Y, so it can be plus 3Y minus 412 times by 3 plus 360 plus 463 plus 463 plus 463, 2985. And now what I can do is, well, I can say I can do minus 49 minus 1486, and then I can do 3y equals my answer plus 2985. So I'm just rearranging it. I'll get 1450, that's 3y. I want a value for the HH bond enthalpy, so only one of them. So I need to divide by 3, and I get 483. Yes, I actually got it right. Because I usually make silly math errors on these type of questions, but in this case, no. You just have to be very careful and go through it step by step. So 483, it does allow 483.3 recurring through 3. Part B says the data book value is this. Suggest one value where why this value is different from your answer to part A. So this data book value is clearly lower. Why? Well, this is bond enthalpy. This is we'll work in this case with mean bond enthalpies. So I'm gonna have to say is that mean bond enthalpies are not the same as the actual bond enthalpies in methanol or in carbon dioxide in this case, and therefore the value is going to be slightly different, so by 2 in this case, 438 to 436, what the data book value says, because they're not the same as the actual values in carbon dioxide, for example, or water, or methanol and water. Suggests one environmental advantage of manufacturing methanol fuel by this reaction. So one environmental advantage is that the carbon dioxide, clearly you can see, is used up. Yeah, carbon dioxide produced when burning methanol is used up in this reaction. Therefore, no contribution to the climate change. We'd only say there's only one mark, so just say carbon dioxide produced is used up in this reaction of burning ethanol or burning methanol. Question part D says you use Le Chatelier's principle to justify why the reaction is carried out at high pressure rather than atmospheric pressure. Well, I can see high pressure, well then it's going to shift to the side with fewer moles of gas, which is the right hand side, therefore I'm going to have more methanol. So that's all I have to really say. and probably waffle a bit more than that, but I'll say that. Firstly, I'll say 4 moles of gas forms 2 moles. 4 moles of gas forms 2 moles. At high pressure, equilibrium shifts to the side with fewer moles of gas. In this example, the 2 moles of gas side. So it moves to the right to lower the pressure, okay, to oppose the high pressure. And what will happen, because you justify this, increases the yield of methanol. Part E says suggest why the catalyst used in this process may become less efficient for carbon dioxide and hydrogen containing impurities. I think this is more on, actually maybe not, on transition metals, acrines, something like that. There's a bit about homogeneous catalyst, heterogeneous catalyst in year 2, and also about impurities. But I guess you should notice impurities will block the active sites, hence the catalyst may become less efficient. And remember, the substrate binds to the active site. And part F, 7 marks. It says laboratory experiment to investigate direction shown in the equation. This much of carbon dioxide, this much hydrogen was sealed. After reaction, this much of yield of methanol was that calculated by Kp, give you answer appropriate number of significant figures. So first thing I would do is I would construct an equation for Kp. So remember Kp is curly brackets. Partial pressure of methanol, products of reactants, divided by partial pressure of carbon dioxide times by partial pressure of hydrogen. But remember, there's 3 moles of hydrogen, therefore it's going to be cubed, if you can see that. So now I need to find out the equilibrium moles. So what I'm going to do here is that's where I'm going to find out the equilibrium moles. ICE, this is the method I always use. I saw some YouTuber go through it. I can't remember properly who it was, but it's somebody who goes through walkthroughs. Very useful. So, got carbon dioxide, I've got hydrogen, I've got methanol, and I've got water. And it tells me initially I've got 1 mole of carbon monoxide and 3 moles of hydrogen initially. So 1 mole of carbon dioxide and 3 moles of hydrogen, yeah. And then it says, after the mixture reached equilibrium, so this equilibrium moles, the yield of methanol is this much moles. So for methanol, I've gone from 0 to 0.86 moles. So I did 0.86. Therefore, with H2O, these are 1-to-1 molar ratio, that's also going to be 0.86. And because I'm adding equilibrium moles in this case, on the right hand side, on the left hand side, remember it's at equilibrium, I'm going to do the opposite. I'm going to decrease it. So with hydrogen, I've got 3 moles, so I need to minus 0.86 times by 3, whereas with carbon dioxide, I've only got 1 mole, so I can just minus 0.86. So 0.14. No 0.42. This is the equilibrium moles. I need now the mole fractions, so M. Well, what I have to do now is I just do 0.14 divided by 0.14 plus the total number of moles. So I get 7 over 1 mole 4. this case, it's going to be 0.42 the moles of hydrogen divided by total number of moles, 0.42 plus 0.14 plus 0.86 plus 0.86. Remember, this is equilibrium moles we're working with. That's 114 for sure. And then 0.86 divided by 0.14 plus 0.42 plus 0.86 plus 0.86. 43 divided by 114. And that's also going to be 43 because that's also 0.86 equilibrium moles. And now all I do now is add them all up to make sure they add up to 1. And guess what? They do add up to 1. If you add them all up, you'd get 1. That's perfect. These fractions, right? So now I want the partial pressure. So what I need to do is I need to times it by the total pressure, and I want total pressure is this. I don't know if I want to convert to pascals or not. I don't think it's necessary because it just wants me to calculate value of Kp. So I can just times by, to find out the partial pressure now, all I need to do is times these values by 500 kilopascals. That can be partial pressure. That's substituted in now. So it's just going to be, I have to keep scrolling up, methanol and hydrogen and water 1-to-1 molar ratio, so I don't need to square anything. So it's going to be 43 divided by 114 times by 500. 43 divided by 114 times by 500. And then I also need to times that by calculator. Times that by 43 divided by 114 times by 500. Divide that by 7 over, remember, include curly brackets, 7 divided by 114 times by 500. And in the calculator, make sure you include brackets as well. Well, carbon dioxide, I've only got 1. It's hydrogen, I've got 3 moles of. Times by 7 out of 38. Times by 500 cubed. Obviously, you'd probably show this because it is 7 marks, so I'd probably write it all down, but it's a waste of time if I do it that in for you guys. So Kp I get as 1.48 times by 10 to the power minus 3. And remember, always try to do it in standard form. And then it says, give your answer program number significant figures, 1.48, that's fine. Give units with your answer. Units now, well, I was using kPa, so it's going to be kilopascals times by kilopascals squared divided by kilopascals times by kilopascals cubed, kPa to the power 4. That will give me 1 over kPa squared. That is the same as kPa to the power minus 2. Hopefully, inshallah, I'm correct. And if I'm not correct, it's whatever Allah wills. And I get, am I correct? I'm correct units, so that's good. And Kp, yeah, it does want you to show it right on the exam paper. 1.483 times by 10 to the power minus 3, yes. Answer must be to 2 significant figures. Must be to 2 significant figures. Tell me in the question. 1.48 times by 10 to the power minus 3. So I would have lost a mark because it wants it to 2 significant figures. So yeah, 1.48. The answer was 1.483, and then I give it to 2 significant figures, 1.5 times by 10 to the power minus 3. But not bad. So 6 out of 7 marks. Not bad. And then question 8 says, which change would alter the value of the equilibrium constant Kp for this reaction? Remember, actually, this is actually very simple because only temperature can affect value of Kp. So, increase the total pressure, that's going to have no effect. It says which change would alter the value. Concentration, no effect. Concentration, no effect. Temperature, boom. Obviously, I just want to go through each one, even though I clearly could see the answer would be D anyway. And that is the end of the equilibrium constant physics and math tutor question paper. And one thing to remember, only temperature can affect the value of Kp.